Going live. Go for it, Bob.
Okay, well, welcome to the second session of PEPM here in virtual Copenhagen. And there's two talks in this session. The first talk is Kenny Liu, who will be talking about control flow obfuscation for featherweight Java using continuation passing. So please take it away, Kenny.
All right, thank you. Thank you, Bob. Okay. Good evening. Actually, from Singapore, so it's evening time here. But I assume that for those folks in European countries, good afternoon to you guys. Hope that you guys have a good lunch. And also welcome back for those friends from back in Japan. All right, so today I'm going to talk about control flow obfuscation. In particular, we are looking into featherweight Java, and we're going to use continuation passing as a means for us to have the obfuscation. So let's look at the high-level code obfuscation. So what code obfuscation is trying to do is that we try to conceal information of the original program without changing its semantics. And the idea is trying to make it difficult for any attacker try to reverse engineer a program, try to unearth some information from your source code, and we try to make it difficult. The means was so over here, I would like to highlight there are at least two main category of code obfuscation. One is called the layout obfuscation, which is kind of simple, where we try to obfuscate the code by renaming variables and method names and package name, just make them harder to read, at least for human being, right? But then there's another category which is called control flow obfuscations, where we try to obfuscate the code or try to hide information by changing the control flow of the original program. So the idea is that to make even like attack that use select analysis even harder. Okay, so that is the idea. Okay, so let's look at the assumptions and a problem here. Okay, right. So we assume that the control flow obfuscation that will be the main player to study here. But we would like to apply it in combination with the layout obfuscation. Let's say, for example, we are talking about Java. Let's say, well, we know that ProGuard is one of the famous tools that apply layout obfuscations. So suppose that we have done that. Okay. So and we also assume that the attacker managed to gain access to the Java bytecode and as well as the source code, because we know that the JVM bytecode is closely resemble the source code. So decompilation effort from the Java code back to the source code is pretty easy, and tools available out there. So which means that the process over here, let's say we started off with the original source code S, and then we apply some layout obfuscation. Let's say ProGuard, we get a S prime here, and eventually you're going to compile to some binary. But then the attacker are able to actually decompile the bytecode back to the source code S prime. And while this S prime might not be so readable by human being, which is programmer, but then the attacker would apply some static analysis techniques, try to recover the control flow of S prime. And the problem here is that the control flow graph of S prime is almost the same as the control flow graph of S, because what we do is just rename the names and stuff, right? So this is pretty much not good enough. Okay, so the objective is that we're going to apply the control flow obfuscation here, okay, so that we obtain a version called S double prime, and this will be compiled into the so-called the bytecode, and we ship to the end user, and any malicious attempt will try to decompile this guy and try to run the control flow analysis on this S double prime, would try to reconstruct the control flow graph. The end result graph or end result control flow graph, okay, will not be isomorphic to the original source code. So that is what we're trying to do here. Right. So let's look at some prior works on control flow obfuscations. And one famous technique is the flattening or control flow flattening by Wang and Hugh and Knight and Davison back in 2000s. So the main idea is basically try to flatten all the nested control flow constructs in a single level branching and looping main control flow. So there's everything merged into one. Okay, so that's the main idea. But the approach that we look at here is actually in a way that is inspired our previous work, I think was published in PEPM 2019. but that approach was using control flow obfuscation by rewriting the source code into continuation passing style. But the targeted language then was using was actually C code, and now we're looking into Java language. Okay. So, but the main idea was from there. So the key idea is that we would like to rewrite, or we like to translate the source program into what we call the Featherweight Java with a lambda in a continuation passing style via source-to-source translation scheme. And all the control flow constructs in the source program, such as sequence of statements, or if else, or loop, and try and catch block will be translated into function calls with high order combinators in the CPS library. Okay, so as a result, okay, the attacks that using control flow analysis, that applying one of the following, for example, you apply a context insensitive analysis or context sensitive analysis with fixed call string. By doing so, they will not be able to actually get a very precise result. I mean, just to show that the result would lose precision. So that's the result that we obtain here. Okay, so let's look at an example how that can be done. So this is the example that I actually we use in the paper. Over here, we define a class called a Fibonacci generator, which has a field, member field, F1, F2, and outpost stand for the last position. So it's like it's a generator. So it's always generating the Fibonacci sequence in a forward manner, right? So there's a constructor here which initializes the 3 member field, and the main work is done in a function called a method called get, which takes in a formal argument x, and which denotes the particular position in the Fibonacci sequence that the user wants to compute, and then it return the result of type int. Okay, so in the body of get, what we have is that we first initialize the 2 local variable I and R, where I is actually a copy of the last positions, and R is the result. We somehow set it to a -1. And then in the next statement, is actually a try-catch block, where in a try-catch block, in the normal execution here, we check whether or not the input x is less than the I, which is the last position. So if so, which means that the user tried to get something that is already have been generated before, and in that case, we're going to throw an exception, right? So that will be handled by the catch clause here, and we'll print out this error message. Otherwise, then we are in this while loop here. Okay, we loop start from where I was in, which is in the last positions, until we reach x, which is what the user asked for. And then we perform this classic of computing the sum of F1, F2, and then swap it with F2 and taking the original value of F2 into F1, and then increment I by 1. And then when we done that, we just remember to record the I, which is back into the last position variable, and we also save the F2 as the result, and then finally return the result. Right, so that is the Fibonacci generator. So if we were to try to actually construct the control flow graph of the get methods, this is what it looks like, right? So as already highlighted in the comments, each of this so-called statements or set of statements denote a simple code blocks in the corresponding control flow graph. Is 1, so 1 is here, okay, and 2 is actually the try catch, and 3 is the if else statement, okay, in case it's true, and then we're going to create the exception and throw it, and it will be handled by the block 8, which is the catch clause, and then it will terminate. And otherwise, if this is not true, and then we're in this branch, this is actually the while loop here, and this is the body of the while loop, and then this is actually when the looping condition is not satisfied, you're going to end up in block 7, which is we capture what is the I back into the L post and the result R, and then we terminate. Okay, so this is the control flow graph of method get. And let's look at how this method get will be translated using the continuation passing style. So over here, we use a target language called FJ lambda, which is a variant of a Featherweight Java, which support nested function declaration, high order functions, and mutable variables in the function closure. Okay. So over here, this is just a high-level translation. So this is you notice that the methods signature is unchanged. Okay, we keep it as what it is, and we leave all the local variable declarations to the top level, so for the outermost level, and we also, in addition, we declare a exception variable for us to capture the exceptions, and the main work is being done in a nested function called get CPS. So this is actually a continuation parsing style version of the get. Over here, this get CPS was actually a lambda term because like I write this as a lambda. So this is the parameter, and this is the body. And of course, in this case, I write in a carry style. And second argument is handle, and the third one is actually the K. So let's look at the type here. So the type of the get CPS is basically it takes in an int, so X is of type int. EXCON is exception continuation, is a type alias here. It takes in a exceptions and return void, so which means that handle is actually a higher order function that takes in exceptions and then return void. So it's the handler. Okay. So notice that in the paper I actually called raise instead of handle, but when I try to rehearse, I realize, well, actually handle sounds better than raise. Well, okay. K is actually the result continuation, okay, which expects a integer and return void, right? So the final result of this get CPS will return void. So the body of the get CPS basically is a application of this horrible or scary function applications. So what it actually does is that we use some a set of CPS combinators in the library, such as seq, which is sequence two continuations together, one after another. Sorry, we try and catch, okay, which actually encode the try and catch block, and if else, which is actually encoding the if else branching, and then loops encoding the loops, and then we use all these helper function to synthesize the original program by chaining up all the individual simple block, such as get1, get4, and get6 and get7. We'll come to what are these get1, get4, get6, and get7 shortly in the next slide. All right. So, and then in the next step here, we just apply this get CPS with the actual input and pass in the handler and the result, okay, capturing the result, and we return the result, right? Okay, so let's look at how all those get1, get4 are actually being generated or being translated. Okay, so we call those simple blocks as those blocks that without control flow statement. Okay, so meaning that they only contain assignment, right? And for example, the block 1 in the original source code is basically this one, right? So we have already lifted the declaration to the outer mode level, so we don't need to care about the declaration anymore, and we just need to focus the translation. So we need to translate these two. So this will be translated into a continuation function called get1, okay, which has the first argument handle, second one is a k. Okay, over here I give the type annotation to the form argument, but they can be omitted, right? So the function get1, okay, is actually a translation result of this block, and it has type CPS fun. So what CPS fun is actually is a function that takes in a exception continuations and another normal continuations, where normal continuation is basically takes a void and return void, and finally return void. Okay, so just to make sure that it reads, it type checks. So this is the handle, and this is the k. Okay, so the body is straightforward. We just like making sure that because all these are within our method, so we just call refer all this to this.lpost, and this well, there's no this is actually constant, so we just copy over here, and then at the end of this function, we just apply the we just invoke the normal continuation k. Okay, so that is the simple block. Okay, another example for block 6. So this is doing the shuffling. Okay, so we compute f1 plus f2 assigned to t, and then we take the old value of f2 into f1, and then we assign new value f2 with the t. Okay, so this is translated in a similar way. Okay, I just omitted the type notation for the formal argument. Okay, so there's no surprise here. Now let's look at the translation for a block 4, which contains a throw exception statement. Okay, in this case, straightforward again, because this is a typical encoding of continuation with continuation passing style. We just apply the exceptions to the handler continuations, okay, or exception continuation. Okay. And for block 5, which is contain a while block, a loop. Okay, so this will be translated into the following. Okay, because we do know that the body of the while loop is actually the block 6. So we have already translated in the previous slides called get 6. And we also know that the conditions, loop condition is I less than x. So we translate it into a delay expression, in the delay in the sense that over here it takes in a parameter n, but this n is nothing more than like a void, right? So we just delay the computation until the loop is actually being executed. So we're gonna when this, okay, so we translate this blocks 5 into a function called to loop that apply to these lambda expressions with get 6 and get 7. So what is get 7? Get 7 is just translation of the block that follows the while block. Okay. Right. So that's while loops. Now we look at the if else, similar. So we have another combination called if else that takes in a delay function that gives us the Boolean test, and takes in the continuation that represent the then branch, which is already translated from here. You get 4, and then the else branch, which is actually the block 5, which is actually the loop we have seen in the last slide. For try catch, we translate into a try catch function call. Okay, try catch is a function that takes in a continuations functions. In this case, it's actually the body in this here, which is the if else together with this speed. So that remember the if else checking for these conditions. In case it's true, we go to 4. Otherwise, we go in the loop, and then the body is 6, and then the loop would actually exit at 7. So that is actually the main computation in the try, right? So in case any of this computation has this exception occurs, we're going to handle it. So this is actually the translation of the handler. So over here we pass in a lambda that use the e here, just rename it, and then we capture it back into the exception variable, and we call get 8 here. Okay. And finally, the sequence. Okay, so in this case, we have the try catch statement here, and then followed by the return. So we have to synthesize this too. So this bit is actually what we've seen in the previous slide. Oops. Yeah, sorry. This is actually the bit that's seen in the previous slide, and the get 9 is actually the return statement here. Okay, the seq is actually the sequence. All right. So let's look at all the combination definition of the combination functions, combinator functions. Okay, for if else, well, straightforward. We are taking in a Boolean test functions. Okay, evaluate if it's true, and then we execute the continuation function that represent the then branch. Okay, otherwise we execute the one that corresponds to the else branch. For loop, is slightly more involved, but still manageable. So we run the we run the Boolean test. Okay, and in case it's true, we're going to execute the visitor, which is actually the body of the loop, and we pass in the handler of the exception continuations, and then as for the normal continuation, we're going to pass in this. Okay, what this is actually, this is a void. Okay, this is the end here will be ignored, is a void, and we make a recursive call to loop itself, and by passing in the same set of parameter. And of course, we also need to pass in the handler and the continuation, normal continuation k. In case the condition is false, we have to get out from the loop. So we call the exit, which is actually the block right after the loop here. Okay, so we say exit. Okay, handle, which is the exception handler, and the k, which is the normal continuation. Okay, for sequence is straightforward. Okay, we two continuations, first and second. So we first execute first with respect to the handler, and now we change the continuation to this functions where expect a void, and then after that we call second with the handler and the normal continuations. Okay, for try catch, we first try to execute the try contingent functions, and then we substitute the handler, condition handler, by wrapping around the handler HDL inside this lambda expression. So we capture the exceptions here, and we invoke the handler with the exceptions, and this would give us a continuation. This would have give us same type as the CPS font, and itself we need to be applied to the handler continuation and also the normal continuations. Okay, and then the K, this continuation is for the try execution. Okay. So that is the translations in a few slides summary. So actually, the actual translation happens on some internal language form. We actually introduce a intermediate language called single static assignment form for Featherweight Java, and which is extended from the work by Ancona and Karadi. We extended their work with exception handling, and the translation just takes place from this one and into the Featherweight Java with Lambda in CPS style. Okay. So over here, this is the syntax of the SSA form for Featherweight Java with exception handling. So the gist here is that like each methods would have a variable declaration and a sequence of block, and each block must be given a label, okay, and followed by a statement. And over here, for simplicity, we segregate the assignment statement from the rest of control flow statement, okay. And the SSA form here restrict that like each variable can only be assigned once, and the merge of the different variable into the same variable by from different branches are done choosing the file assignment. So, for example, we will see later on that there are some cases that we have to create a alias for multiple alias of the same variable and for different branches, and then we need to perform a merge. Okay, so for example, for if else, we have to put a merge or join, okay, a find statement at the end, okay, because the variable that assigned to in the then branch and the else branch might be first, but we have to somehow need to merge them here at the end. Similarly for while loops, because the join would have to happen before the check for whether or not the condition should proceed or not. And then the interesting thing here is that for the try catch block, we have to have two assignment here. One is right before the catch. This is because that for the try block, the normal block here, there might be multiple blocks. So the exception can occur in any of these blocks, any possibility. So we have to handle all kinds of location where the exception might be thrown. So we have to perform a join here, okay, right before the catch. And then the other one, of course, after the normal execution and the catch clause. Okay, so this is the second join. Okay, and this is the get method in SSA form. All right, so I will not go through detail because for time constraint. So there's only 2 minutes left. So, and I also skip the syntax for the FJ lambdas. So this is the translation. The translation is done in some kind of denotations, syntax. So I will skip it here because I already walked through the translation by the example in earlier slide. Okay, and so finally, before I actually wrap, I just want to touch on the potency analysis, because we want to make sure that our translation is effective against the attack that using control flow analysis. So let's look at the context-insensitive control flow analysis. So we use the capital lambda to denote a set of all possible lambda values, and we form a lattice. So these analysis here is that we operate on some abstract state, where the abstract state is basically mapping from the program variables, all the program variables, into sets of lambdas, right? And these are then we can define the flow functions as following. A flow function basically takes in a statement, and takes in a state and gives us a next state. Okay, so here are a few selected definition for the flow function here. And for for if else it's simple because it doesn't change the state. For assignment, this is assigning constant to the variable x, and we basically assign x with the empty set. And in case we are assigning a lambda expression to x, then of course we update the state with x that is assigned to a singleton set containing the lambda. All right, so and so forth. Okay, so if we apply to the running example that we've seen earlier on, which is the get function, we get, and then we can basically get a mapping from all the program variable to the set of possible lambda expression that they potentially bound to. And then we do know that where are those variables are actually called, invoked and used, and we can then define a global, or we can reconstruct a global control flow graph as the following. Okay, but then the observation here is that we lose precision. Okay, because as we can observe that there are more than one cycle. Like one cycle is coming from here, and there's another cycle start from here, then going through and back here. So which means that there are two loops here, but when we recall earlier in our original source code, there's only one loop, and over here now we have two. So the observation is because that the function's loop is actually a recursive function, and we do know that this is a limitation with context insensitive control flow analysis, and we actually make multiple calls to the loop functions. So therefore, this cost at the cost of the precisions. Okay, we try to also try to play with the context-sensitive control flow analysis, and try to train the context. And we try the context with, let's say, the call string. Okay, with fixed size, and we define the context with the last calls aside of the functions. And then we try the same strategy, and then we find that actually the precision is still not good. It's still losing some precisions. Okay, so this is my last slide. In summary, we presented a control flow obfuscation technique via condition parsing translations. We handle the language is Featherweight Java with exception handling, and we phrase the obfuscation technique as a source-to-source translation from Featherweight Java, as I say, with exception handling to a Featherweight Java lambda. And we have done some potency analysis to show that like this approach is effective against certain set of control flow analysis. Okay, future works, we're still working on the implementation and some benchmark, and we also want to work on the proof, make sure the translation is correct. And of course, we want to explore some other control flow analysis method as well. Okay, so that would be the last slide that I want to talk about. So any question?
Okay, thank you very much. Does anybody have any questions?
Yeah, I have one. So one of the things you want of an obfuscator is that it does not slow down the program very much and doesn't use too much extra memory. I can see you haven't implemented it yet, so you can't really show us any benchmark, but what are your expectations in terms of extra resources needed in the obfuscated program?
Okay, so first of all, yeah, like what you said, I don't have an implementation, but based on what I observed previously in the implementation that I've done in the PEPM 2019, even though it's a slightly different transformation, but the targeted result is also a language that using CPS style. We do see the part that without the recursive call to the loop is we do have some constant so-called overhead because of we need to doing some extra bookkeeping, handling those memory allocations. And whereas in case there's a loop, and of course we're going to need to have the make a call to recursive call to the loop functions, and potentially there might be a costing extra so-called the call stack space. Yeah, so that's what we can foresee.
Yeah, I have another short question, if that's okay. So there have been published methods to convert back from continuation parsing style to direct style. Do you think your method will be vulnerable to such transformations?
Actually, it's a good question. Actually, I have done some review on the approach. So let's say it is possible that let's say the attacker are aware of this obfuscation technique, that, well, let's try to reverse engineer by undoing these continuation parsing stuff. So for instance, we can actually apply what Olivier's approach, okay, and suppose we ignore the treatment of exceptions, okay. So one can actually like translate the loop combinator back in CPS style back into direct style as follows, right? So now the loop will become like this. So it become like this, and then we just gave it all the continuations stuff. Still have the visitor and the exits, and then the loop will call itself. But as you can observe that we could have still using this one in our obfuscation, because now this loop is actually recursive functions, and which means implies this for same observation that applies, because like we try to apply a control flow analysis with in a program that use this loop function, we still lose precisions. So, but then you argue, why do I use continuation parsing here? It's because I think it's more for convenience to handle exceptions.
Okay, thank you.
Okay, thank you. There is another question on YouTube, but it's got a kind of 30-second answer. It's kind of related. How to measure how well programs are obfuscated by the CPS translation?
I'm not sure how to quantify how well. I actually it's basically what I'm trying to argue, that the potency analysis. I mean, like for now, I'm able to look at least two kind of control flow static control flow analysis that try to render them like having imprecise results. So that's what I can do at the best for now. But of course, in future maybe I can try to look at other methods as well. Okay. So I'm not sure whether I'm addressing the question.
Yeah, I'm not sure how to. Okay, thank you very much. And Peter, do you want to, or can you unshare and then? Right.
Thank you.
I'm not quite sure how to do this. Hi, Peter. Can you share and unmute yourself? So our next speaker is Petr Lozov on an efficient, fair conjunction for structure-recursive relations. Take it away, Peter.
Can you hear me?
Yes.
Cool. Can you see my slides?
Yes, we can see your slides. Yep.
Cool. Okay. Hello, everyone. Hello, everybody. My name is Petr Lozov, and this talk is about fair conjunction in relational language mini-canron. Mini-canron is a relational language that allows one to declaratively describe problems in the form of logical formulas or goals. One of the basic operations in mini-canron is conjunction. It allows one to find common answers for several goals. In conventional mini-canron, conjunction is left-biased. In other words, the conjunction necessarily evaluates the left conjunct. The right conjunct is evaluated for each answer of the left conjunct. Thus, the order of conjuncts is critically important due to this asymmetric nature of the conjunction evaluation. The search for answers in mini-canron is complete, and the order of conjuncts doesn't affect search completeness. However, the order of conjuncts often affects both performance and convergence. Let's consider an example. This is the list sorting relation sorter. The symbol O above the name of the relations is a standard convention for miniconron. This relation has two arguments, X and Y. The first argument is an arbitrary list, and the second one is sorted version of the list. The topmost operation in the relation is candi. This operation is a disjunction which unions the sets of answers from a list of goals. In the first disjunct, we consider an empty list case using unification. In this case, the sorted list is also empty, and we connect both constraints using operation conjunction. In the second disjunct, we consider a non-empty list. To do this, we need 3 additional fresh variables, which we introduce using the construct fresh. In this case, we are separating the first element from the sorted list using unification. This element is the minimum in the list. Then we eliminate the minimum element from the original list using the relation smallest. And finally, we sort the reduced list using a recursive application of sorter. And we connect 3 constraints using conjunction. In this relation, we have 2 nested applications, smallest and sorter. It's unclear which order of these conjuncts we should choose for better convergence and performance. So let's consider both orders of sorting a 4-element list. The operation run is used to execute relational queries. This operation searches for the values of the query variable. In our case, it's Q, for which the query is true. Run asterisk search for all possible answers. In the first case, we have 1 answer, after which the evaluation completes. The only 1 answer is expected because the sorted list is unique. In the second case, we also have 1 answer, but then the evaluation diverged. Thus, we have correct answer, but not the proof of the uniqueness. Okay, let's simplify the query. The operation run with number n search for the first n answers. In our case, n equals 1. Now the query converged in both cases, but the performance of the second query is several times worse than the first one. And if we try to sort a 5-element list, then in the first case, the performance hardly changes. But in the second case, we are getting no answer even after 5 minutes of waiting. Well, our goal is to introduce a fair conjunction for miniconron. In other words, we want the conjunction to depend as little as possible of the order of conjuncts. It seems that it would be enough to require that the order of the conjuncts does not affect the convergence in the conventional miniconron semantics. However, there are examples when in the conventional semantics a query diverges in any order of conjuncts, but it can converge with a more flexible order of evaluation. Let's consider an example. The first relation repeater is true only if all elements of the list L are equal to the expression E. And the second relation, divergence, requires that the elements of the list L be equal to two different constructors, C1 and C2, at the same time. Only one list satisfies these constraints, the empty one. Let's try to evaluate all the answers. We start with the application divergence. We unfold this application and get the conjunction of two application repeater. Next, we unfold the left conjunct and get two disjuncts from the body of repeater. In the first disjunct, the list is empty. In the second, it is not. The second application repeater remains in both disjuncts. Next, we unfold the left conjunct of the left disjunct. And also, we rearrange the disjuncts. This is a necessary step in the conventional semantics, which provides the completeness of the search. The next application we unfold is the same as the application we have already unfolded in the second step. Indeed, its first argument is a constructor C1, and its second argument is a free variable as here. This loop causes the evaluation to diverge. Moreover, this query will diverge for any order of conjuncts in both our relations. But instead of changing the static order of the conjuncts in the relations, we can change the dynamic order of evaluation conjuncts. For this, we have developed angelic semantics of Minikanran. This semantics considers all orders of conjunct evaluation in a non-deterministic way. This semantics has a larger step than the classical semantics of Minikanran. Instead of performing one atomic operation, one step is unfolding a relation application. And the evaluation converges if at least one of the orders of evaluation conjuncts converges. Divergent evaluation discussed earlier is one of the orders of evaluation in angelic semantics. But at the same time, we have another order of evaluation. The first few steps are the same as in the previous evaluation. But at this step, we can choose the right conjunct instead of the left one. As a result, this disjunct will be refuted by contradiction, and the evaluation of the second disjunct will be converged in one step. Thus, this query converges in the angelic semantics, but diverges in the classical one for any order of conjuncts in the relations. However, angelic semantics is non-deterministic. Consequently, it's inefficient in practice. Therefore, we use it only to define the notion of fairness. The semantics is fair if the convergence of an arbitrary goal is equivalent to its convergence with respect to the angelic semantics. We have developed a parametric semantics which, instead of considering all orders of conjuncts evaluation, does only one. This order is determined by the parameter, the predicate P. This predicate takes substitution theta, relation application R, and application history H. The application history H is a list of the application that gave rise to the application R. At each step, we choose the leftmost application for which the predicate is true. So we can define different semantics using different predicates. The simplest predicate is the constant true. In this case, we get the conventional left-biased semantics, which always unfold the leftmost conjunct. A more interesting predicate is the uniform predicate. This predicate unfolds a conjunct no more than n times, and then go on to the next one. This behavior is similar to the disjunction behavior, which reorders the disjunct after each step. Let's go back to our example. Now, the query of all answers with run asterisk converges in both cases. Moreover, in the second case, we get a huge performance improvement for n equals 11. But it's still worse than in the first case. Also, if n is not 11, then the performance is much worse. So, on the one hand, the uniform semantics is a fair semantics. And it has better convergence than left-biased semantics of Minikanran. Also, it demonstrates a better performance for a fine-tuned n. But n is, however, we need to choose n for each program. And different conjuncts require different values of n. But n is global for a whole goal. And we can switch the next conjunct in program to early or too late. So we want to dynamically determine when we need to switch conjuncts. To do this, we first define a class of fair semantics and then select one of them that is efficient in practice. We want to prohibit the endless evaluations of the one conjunct. To do this, we use the notion of well-quasi-ordering relations. Well-quasi-ordering relation over the set X prohibits infinite sequences in which there is no pair satisfying the relation. We can define well-quasi-ordering predicates using a well-quasi-ordering relation over the set of pairs of substitutions and applications. The predicate is false while current application and all the application from the history aren't in the relation. And the predicate is true if the current application and some application from history are in the relation. As a result, any well-quasi-ordering predicate excludes the possibility of an infinity history. Therefore, it prohibits the infinite evaluation of one conjunct. We have proved that the semantics based on the well-quasi-ordering predicate is fair. Thus, we have got a whole class of fair semantics. Now we define the semantics from this class, which is efficient in practice. To formulate the predicate for our semantics, we need the definition of structural recursion. An argument is structurally recursive if it is structurally decreases with each recursion step, and relation is structurally recursive if it has at least one structurally recursive argument. For example, let's consider the relation appender to append to list. Arguments x and z are structurally recursive. Indeed, xs is subterm of x and zs is subterm of z in a single recursive application. This means that they will structurally decrease with each recursion step. So appender is a structurally recursive relation with two structurally recursive arguments, x and z. It's enough for us to define a well quasi-ordering relation in order to obtain fair semantics. We want the conjunct to be evaluated while its structurally recursive argument decrease. Indeed, if structurally recursive arguments start to grow, the relation no longer performs case analysis, but starts to explore multiple branches simultaneously, enumerating all possible values for structurally recursive arguments. So we define the well quasi-ordering relation based on the heights of the structurally recursive arguments. While the heights of the structurally recursive arguments decrease, we continue the evaluation of the conjunct. As a result, we get fair semantics by structural recursion. And this is our example again. The query for all answers converges in both cases. Moreover, we have the same performance in both cases. The second query is evaluated identically to the first one. This is because fair conjunction immediately switches the conjunct smallest. To summarize, this semantics is fair, and it has better performance than the left-biased and uniform fair semantics. It instant switches conjuncts in case of uninformative structurally recursive arguments. But if a relation isn't structurally recursive, our approach degrades to the uniform fair semantics. Let's talk about evaluation. We used 5 benchmarks for evaluation: list reversing, list sorting, and 3 more complex programs. These are 3 solvers of classic math puzzles. Also, each benchmark becomes in 2 versions. In the optimistic version, we have manually selected a good conjuncts order. In the pessimistic version, we put several conjuncts in a bad order. The first solver is the Tower of Hanoi solver. The puzzle consists of 3 rods of a number of disks of different sizes, which can slide onto any rod. The objective of the puzzle is to move the stack to another rod, obeying some simple rules. The second one is bridge and torch problem solver. This puzzle deals with 4 people, a bridge, and a torch. These people have different speeds, and they must cross the river in pairs and with a torch. And the last solver is water pouring puzzle solver. The puzzle deals with a finite number of jugs of certain volumes. It's necessary to obtain a certain amount of water by steps of pouring water from one jug to another. These solvers are quite complex to implement in Mini-Conron. Instead of an explicit implementation, we have developed simple decision verifiers in a functional language ACAML. Then we got relational solvers using relational conversion. As an example, let's consider the problem of searching a path in a graph. Instead of explicitly solving this problem, we implement a verifier if the path belongs to a graph. The relational version of the verifier has an additional argument corresponding to the result of the original function. We can use this verifier, relational verifier, to generate all paths if we define the graph and the result and leave the path as a free variable. Moreover, we can generate a path between given vertices if only define the starting and ending vertices in the path. Let's talk about the evaluation. In optimistic case, the fair conjunction produces additional computations, which adds a small overhead here. However, even manually selected conjunct ordering is sometimes less efficient than dynamic conjunct reordering, for example, here. Let's talk about pessimistic case. First of all, if the column reaches the top, then this benchmark didn't complete in 5 minutes. In this pessimistic case, left-biased semantics and even uniform fair one slow down dramatically. At the same time, fair semantics by structurally recursion demonstrates comparable performance to the optimistic case. You can find out more about the fair conjunction in our paper. We described formal angelic semantics for Mini-Conron, and also we described formal parametric semantics for Mini-Conron. Next, we use this one to express left-biased semantics, uniform fair semantics, and fair semantics by structural recursion. And finally, we presented more detailed evaluation and the proof of fairness. In future, we plan to generalize our approach for a larger class of programs. We also plan to formalize our approach in Coq Proof Assistant. Finally, we are going to apply this approach to disjunction of Mini-Conron. That's all. Thank you. Thank you.
Okay, thank you very much. Should we thank Petr? And does anyone have any questions? Keeping an eye on Zoom. Yes, thank you, Torben has one.
Yeah, so you use the height as the well quasi-order, but that's a fairly crude notion of a well quasi-order. There are lots of different well quasi-orders that are more precise in the sense that they allow longer sequences that are safe. So, for example, homomorphic embedding would allow larger sequences. So have you considered other measures for your well quasi-order?
Yeah, thank you for your question. Yes, we tried a lot of different well quasi-ordering relations. Some of these needs a lot of time to calculate result of well quasi-ordering relation. And in this case, we have a big overhead when we evaluate relation query. Another problem, some well quasi-ordinary relations don't help to find good order of conjunct evaluations. As a result, we just evaluate different well quasi-ordinary predicates and choose the best one.
Okay, thank you.
So any other questions?
I have a question, if no one else does.
Yeah, that's on.
So you get this like significant speed up if you are able to take advantage of structural recursion. I wonder if you've considered examples where you actually refactor your program in order to introduce structural recursion, and if you then see a significant speed up. Have you done that kind of experiment?
No, we don't do this experiment.
It might be interesting to try. I mean, it's just a typical thing that well, I don't know, people who are trying to use total languages often do. You write your program and Agda or something won't even accept the program at all unless you give it some sort of structurally recursive measure. But yeah, maybe doing that kind of refactoring would also enable your speed up. I don't know. Might be something to try.
I see, yeah.
Okay. I had one just final question on your future work. You said a larger class of programs. Could you say a bit?
Yep. As I say, our current approach works with structurally recursive relations, but not all of relations are structurally recursive. And we want to generalize our well quasi-ordinate predicate to more class of relations. For example, we can detect quasi structurally recursive arguments. It's arguments which structurally decrease in not in all branches of relation, but in almost branches. So in yep.
Okay, so that would make more programs amenable to this technique.
Thank you.
Okay, thank you very much. I think that's the end of the session. Let's thank Petr again. And I believe the next session is well now in 26 minutes.
That's right.
We'll be invited to talk from Zhuo about PEPM or program manipulation in C.
Yeah, and also you should come along to that session as well, because at the beginning of the session I'll be announcing the best paper award briefly before we introduce Julia. And in the meantime, we should go back, well, take a break or whatever, but go back to Clouder. And maybe some of us could actually try meeting on Clouder. We quite often seem to have people in the room on Clouder, but not actually with their video on or anything. But yeah, see you back for the keynote in 25 minutes. Thanks. Oh, I should stop the stream as well. Okay, so that should have stopped streaming.